Hi, I'm Antonella Vietri and I'm going to talk about the analysis of the poroviscoelastic behavior of covalently cross-linked hydroxyl cellulose for biomedical application. Most of this thesis work was carried out in Sweden at Chalmers University of Technology during my Erasmus project. We can start from the definition of hydrogels. Hydrogels are three-dimensional polymeric networks capable of absorbing large amounts of water. They can be categorized into types: chemically cross-linked and physically cross-linked hydrogels, depending on the nature of the polymeric network. If the polymeric chains are interconnected by cross-links through strong covalent bonds, we have chemical hydrogels. Otherwise, in case of physical bonds, we talk about physical hydrogels. Hydrogels have different fields of application. They can promote the wound healing. They can be used for producing contact lenses, in drug delivery, tissue engineering, and cell culture. In this work, the use of a hydrogel is connected to the treatment of the low back pain. The intervertebral discs consist of two parts: the annulus fibrosus, a structure made up of collagen fibers, and the nucleus pulposus, which is filled with a gel-like elastic substance. With age, the nucleus tends to dehydrate and shrink in size, decreasing the space between vertebrae and generating the low back pain. Due to similarities in their composition, hydrogels could be used as scaffolds for tissue engineering on the nucleus pulposus. For this reason, it is fundamental to determine the mechanical properties of the gels. This can be done through static tests, that is, tension, confined or unconfined compression, indentation, or dynamic tests, such as the shear geometry. When a gel is deformed, it behaves in two different ways. If the relaxation is due to the local rearrangement of polymer chains, we talk about viscoelasticity. Otherwise, when the migration of the solvent allows the gel to relax the deformation, we have the poroelasticity. The former effect doesn't depend on the gel size, while the latter is size-dependent. In literature, it is claimed that it's possible to separate the viscoelastic effect from the poroelastic one at different time scales in a test by performing tests parametric in the diameter of the gel. Different mathematical models have been used to characterize the hydrogel's behavior, which can be categorized into approaches: the multiphasic and the monophasic approach. According to the multiphasic approach, the gel is conceived as a set of different phases: the polymeric matrix, the interstitial water, and the possible presence of other species. In this case, the coexistence of many phases makes this approach arduous to manage. On the other hand, the monophasic approach considers the gel as a single phase in which multiple species can coexist. It is built on strong thermodynamic basis, and it will be chosen in this work to implement the poroviscoelastic model. The general objective of this thesis is the characterization and modeling of the poroviscoelastic behavior of covalently cross-linked hydroxyl cellulose. The intermediate aims are the mechanical characterization of the half gels, the evaluation of the effect of the cross-linker amount together with the effect of the diameter, the description of the poroviscoelastic behavior of hydrogels through a mathematical model, and finally the comparison of modeling predictions with the experimental data. After the introduction, the materials and methods used will be described, an overview of the poroviscoelastic model will be shown, and finally results and discussions, together with the conclusion, will be presented. The HEC, the hydroxyl cellulose, is a cellulose derivative obtained by replacing hydroxyl groups inside the molecule with hydroxyl groups. The divinyl sulfone has been widely used to cross-link cellulose derivatives. The hydrogels were made starting from a 5% of HEC solution. The solution was diluted to half of its original concentration by adding a solution of sodium hydroxide in order to have a pH of 12, because at this pH the cross-linking reaction is promoted. Then, a prescribed amount of dinyl sulfone was added in order to have three different weight ratios, HEC-DVS, as shown in the table. Rheological measurements were carried out using a rheometer with a parallel plate geometry. In particular, a frequency switch test was performed, keeping the deformation at 5% and changing the frequency in a range of 0.1 and 0.5 Hz at 20 degrees. During the stress relaxation test, a certain strain is applied and kept constant over the time, while the stress is monitored during that time. In this work, both the unconfined and the confined compression were performed. The confined device consisted of a big chamber where the sample was placed. In the bottom of this chamber, a porous filter and below it drilled holes were present to connect the chamber to a channel filled with water in order to allow the leakage of the solvent when the compression was carried out. The weight of the gel was monitored in 3 points: at the end of the cross-linking reaction, after the gel spent 24 hours in large excess of water, and at the end of the stress relaxation test. It has to be clarified, as shown in the picture, that during each test, the gel was deformed with a sequence of increasing strains, and therefore the third point corresponds to the weight of the sample when the highest strain was applied. Finally, the percentage of water absorbed or released from the gel is calculated using this formula. To derive the equations of the model, a Lagrangian approach was used. Here, the mass and the momentum balance are reported where C1 is the water concentration and P is the first Piola-Kirchhoff stress tensor. The constitutive equations can be obtained through the dissipation inequality. According to it, not all the conventional power expended on a region can be converted into change in the net free energy, because a portion of that power must go into dissipation. A relaxed version of the hydrogel free energy had been used, where the Helmholtz free energy is reduced by the volumetric constraint by means of a Lagrangian multiplier P that stands for the pressure field. On the other hand, the Helmholtz free energy is the sum of two contributions: the elastic term, which is derived from the affine network theory, considering as rheological model a standard linear solid model, and the mixing contribution that comes from the Flory-Huggins theory, where K12 is the Flory-Huggins interaction parameter. Once obtained the equations of the model and the constitutive equations, the initial condition of the gel had to be specified. The gel was considered in equilibrium with the external solvent and in a stress-free state condition. Therefore, the initial pressure P0 could be derived, and from the equilibrium condition with the external solvent, the value of K12 was acquired. The boundary conditions will be presented for the specific cases. Oscillatory measurements show that the higher is the Hess-DDS ratio, the higher is the value of the storage and loss modulus. In addition, G' is frequency independent and always greater than G2. This indicates a predominant elastic character and low viscous properties of the Hess gel. Then, in order to switch from the frequency to the time domain, the relaxation modulus was derived first from the experimental values of G' and G second, and then it was fitted with the value of G coming from a standard linear solid model. The results are shown in the table, and the values of G1 and G2 will be used as starting values for the optimization of the polo viscoelastic model. At the end of the cross-linking reaction, a water loss together with the shrinkage of the gel were recorded. These gave rise to different values of the water mass fraction at the end of the reaction and also after the swelling. In addition, a trend was found. Increasing the Hess-DDS ratio, the swelling capacity decreases. In this table are reported the test conditions. Different parameters have been changed: the polymer cross-linker ratio, the type of experiment, confined or unconfined, the test duration 600 or 10,000 seconds. Then, to evaluate the poroelastic effect, unconfined tests parametrically in the diameter for 10,000 seconds were carried out, while to compare the confined experiment with the unconfined ones, short-time tests for 600 seconds were made. A sequence of 4 increasing strains was performed in the unconfined case, while 3 strains were applied in the confined one. The long-time range tests revealed the photoelastic effects. The stress relaxation curves, as shown in these graphs, are size-dependent, and the relaxation is due to the regression of water as reported in the following table. Furthermore, the smaller is the gel diameter, the higher is the percentage of water released. In the short-time range, instead, the curves are similar and independent on the gel size. So, some tests were made for 600 seconds in order to evaluate the cross-linker effects. From the graphs, it is clear that increasing the degree of cross-linking of the HEC, the stress recorded is higher, and the little level of relaxation is due to the intrinsic viscoelasticity of the network. The same criterion was adopted for the confined experiment. In this case, the same trend of the unconfined test is shown. The higher the amount of DBS used, the higher is the stress. But the stress recorded for the confined tests are not dramatically different from the unconfined ones. This can be due to a non-perfect confinement because of a non-perfect matching between the chamber and the gel, which would allow a certain amount of radial expansion during the compression. The boundary conditions in the unconfined case consider the gel in contact with the external solvent on the boundary gamma free and free to expand in the axial and radial direction. Gamma 1 is the axis of symmetry, gamma 4 is the basement of the instrument, while gamma 2 is the part in contact with the probe, that is deformed axially with a velocity v, and this star corresponds to the time needed to apply the desired strain. The first step consisted of an optimization procedure on the parameters G1, G2, and tau, considering that for the short time range test, the gel shows the viscoelastic effect, so the diffusion coefficient was excluded in that case. The values obtained from the model have the same order of magnitude of the parameter from the standard linear solid model fitting. Then, the key 1, 2 value were evaluated, showing that for each HEC-DBS ratio, it was higher than 0.5, that indicates a non-good interaction between the polymer and the solution and the solvent. In order to verify the reliability of the parameter obtained, a simulation for the other strains was performed. The predictions were satisfying for the 6 and 12%, but not for the 25%. This can be due to a permanent deformation experienced by the sample at the end of the increasing sequence of strains. In case of longest tests, a simulation on the diffusion coefficient equal to 10 to minus 6 square meters per second was made. The model seems to be able to predict the relaxation for the diameter of 12 and 20 mm, as reported in the table, but the results were not satisfying for the smallest size of 5 mm. Then, a parametric study on the diffusivity was performed. For each diffusion coefficient, the model describes a lower level of relaxation. This may be due to errors in the experimental determination of the diameter and to a non-good control of the cross-linking reaction. For the confined test, the boundary conditions are the same, except for the boundary gamma 3, where the gel is confined, and on gamma 4, which is the part in contact with the external solvent through the filter. A parametric study on the diffusion coefficient again was implemented. The results were not satisfying, showing the importance of the kinetic of the water transport in this kind of tests, and confirming the hypothesis of a non-perfect confinement. In fact, this reduces the recorded stresses, and as a consequence, in the model, higher diffusivities have to be used. From the experimental results, it can be seen that the HEC gels have a predominant elastic character and low viscous property. The higher is the amount of crosslinker used, the higher is the gel stiffness. It is possible to separate the viscoelastic effect from the poroelastic one, changing the diameter. The poroviscoelastic model represents a good tool in the description and prediction of the experimental data. Then, in the future, further investigation about the cross-linking reactions should be done. An increasing sequence of strains on each shell should be avoided. The gravimetric measurements should be repeated at different times in order to have more information about the diffusion of the water. A perfect matching between the sample and the chamber should be ensured. Then, further improvements for the model can concern modification of the boundary conditions and the theory on which is based the elastic contribution. Thanks for the attention.